This session is about molecular orbital theory. In the previous session of molecular orbital theory, I discussed energy level diagram and 5 examples I solved. In a molecular orbital theory of molecules, first we used to write the electronic configuration, we calculate number of electrons, we used to draw energy level diagram, then we write electronic configuration, we calculate bond order, and then we predict the magnetic property of that. This is the stepwise we learnt about molecular orbital theory of molecules. Now I am going to move with some other examples of MOT. Example number 6, nitrogen molecule. So let me write here, the 6th example is a nitrogen molecule. So one nitrogen combines with one more nitrogen, we get nitrogen molecule. Nitrogen atomic number is 7. Therefore, the electronic configuration is 1s2, 2s2, 2p3. This nitrogen electronic configuration I am writing 1s2, 2s2, 2p3. So this nitrogen has 7 electrons and one more nitrogen atoms has 7 electrons. Therefore, nitrogen molecule contains 14 electrons. So these 14 electrons has to be distributed in energy level diagram. I have here energy level diagram, and these 14 electrons has to be distributed because nitrogen molecule contains 14 electrons. So as we have seen the energy level diagram and what will be the energy sequence of that, and I hope you know the energy sequence will be in this fashion. The energy is going to be increased in this fashion. So bottom to top energy of the atomic orbitals is going to be increased. So we have a 1s atomic orbital, 2s and 2p. You need to consider these atomic orbitals and you need to know how to name these. So this is the section of 1s atomic orbital. So this is 1s and this is also 1s. I hope you remember these are atomic orbitals, and in the right side these are also atomic orbitals. In between we have molecular orbitals. When atomic orbitals combine, we get molecular orbitals. Two types of molecular orbitals, BMO, ABMO. BMO will be of lower energy, ABMO will be of higher energy. Similarly, this is BMO and ABMO. These three are BMO and these three are ABMO. We know this. So therefore 1s I am going to write, and here this is sigma 1s and this is sigma star 1s we are going to get. The second one will be 2s atomic orbital, 2s atomic orbital, sigma 2s we get here, and this will be sigma star 2s. This is for the 2p and this is for the 2p. So px, py, pz actually, and this is also px, py, pz. So 3 BMO we have and 3 ABMO we have. So out of these 3, 1 will be sigma and 2 will be pi. So these are actually pi to px and this is pi to py. So these two are pi to px and to py. The energies of these two are identical, and we get here sigma to pz. Sigma to pz. So these three are the BMOs. So ABMO I will write, these two are again 2px 2py, but that is anti-bonding. Therefore pi star 2px I write here, and this will be pi star 2py, and this will be sigma star 2pz. So this is how we name the atomic orbitals and molecular orbitals. We have to distribute 14 electrons. So first we will consider 1s2. So in 1s2 we have 2 electrons. So 1s2 of this and 1s2 of this. So 1s has 2 electrons. We know electrons of opposite spin can only be paired according to Pauli's exclusion principle. 2 electrons we have. In 1s section only, total number of electrons will be 4. So therefore I am going to fill this. So first lower energy level has to be filled. So 2 electrons we get here and 2 electrons we get here. K shell is completely filled. Remember that 1 is the first main shell, K shell. 2 and 2 will be the second main shell, that is L shell. K shell is completely filled now. Now now we'll talk about this 2s2 and this 2s2. In a 2s2 we have 2 electrons, and here in this 2s also we have 2 electrons. Totally 4 electrons has to be distributed in these 2 molecular orbitals. Of course it is very easy, I distribute the 4 electrons in this case. So now we'll come to 2p and 2p. Try to know, in a 2p we have 3 electrons, in this 2p also 3 electrons. So 3 electrons has to be filled here and 3 electrons has to be filled here. Remember, you need to follow Hund's rule. So all the atomic orbitals are filled with 1 electron each. After that, pairing of electrons starts. So 3 electrons we have, and each electrons I am going to fill in 1 atomic orbital, and here also I fill the 3 atomic orbitals with 1 electron each. So 2p3, 2p3. So in 2p section we have 3 electrons, here we have 3 electrons, totally 6 electrons we have. So 6 electron has to be distributed in this section. So 3 are BMO and 3 are ABMO. First lower energy level filled first, and later higher energy has to be filled. So 6 electrons. These 2 molecular orbitals are of identical energy. So Hund's rule you need to follow. So out of 6, 1, 2. Okay. Next 3, 4. So it is over. Now 5, 6. So 6 electrons we filled here. So all the electrons we have in BMO, but we don't have any electrons in ABMO. So this is how you need to fill atomic orbitals, and from combining that we are supposed to fill molecular orbitals. So now we'll write the electronic configuration of nitrogen molecule. So electronic configuration, and as we know in MOT we consider molecular orbitals for writing the electronic configuration. So here sigma 1s, sigma star 1s both are completely filled. You can write sigma 1s2, sigma star 1s2. Since K shell is completely filled, it does not take part in bonding also, you can say. So instead of this I can write K and K. You can write this one because 1s2 and these 2 are completely filled, K shell, K shell. So this is the 1 molecular orbital of K and this is the 1 molecular orbital of K. So K shell and K shell is filled. So now we have sigma 2s. I am going to write here sigma 2s. In sigma 2s we have 2 electrons. The number of electrons we write superscript, and the next energy level we have sigma star 2s. In that case also we have 2 electrons, and later we have these 2 of identical energy. You can write any one first. So pi to px we have 2 electrons. I am going to write over here. Then pi to py and 2 electrons we have, and later we have a sigma to pz. So sigma to pz 2. So if you count the number of electrons, that would be actually 14. So this is how we write the electronic configuration, and now we'll calculate what would be the bond order here. We have a formula to calculate bond order, that is 1 by 2 into NB minus NA. So NB, number of electrons in bonding molecular orbitals, and I hope you remember what is the place of a bonding molecular orbital. I will show you here. This is the bonding molecular orbital, this is the bonding molecular orbital, and these are the bonding molecular orbitals. So how many electrons we have? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In a BMO we have 10 electrons minus number of electrons in anti-bonding. So these are the anti-bonding. 1, this is anti-bonding, this is anti-bonding, and these are also anti-bonding. So in anti-bonding 1, 2, 3, 4, and we don't have any electrons here. 4 electrons I am going to consider here. So 10 minus 4, 6. 6 divided by 2, we are going to get 3. And what this indicates? So in between 2 nitrogen atoms we have 3 covalent bonds, triple covalent bond. As we know, bond order is nothing but number of covalent bonds present in between the atoms. So since we got bond order as 3, therefore in between 2 nitrogen atoms, because N2 is a molecule, so in between 2 nitrogen atoms we have 3 bonds or triple covalent bond, you can say. What about the magnetic property? As we know, magnetic property depends on the presence or absence of unpaired electrons in molecular orbitals. So if you consider molecular orbitals and all the molecular orbitals are completely filled, or I can say we don't have any unpaired electrons here. So since we don't have any unpaired electrons, therefore this molecule is diamagnetic in nature. This is diamagnetic in nature. So this is how molecular orbital theory of nitrogen molecule can be explained. Example 7, N2 plus. N2 plus is ion. So till now we discussed the MOT of molecules. So now we'll see what is the change we have to do if you have ions like N2 plus ion. So first we'll see how many number of electrons we have. As we know, nitrogen molecule is formed by combination of nitrogen atoms. Nitrogen atomic number is 7, therefore electronic configuration will be 1s2, 2s2, 2p3. For this nitrogen also 1s2, 2s2, 2p3. So total number of electrons will be 14 electrons from this nitrogen atom and this nitrogen atom. 7 electrons we have. Totally in a nitrogen molecule we have 14 electrons. But remember, we don't have nitrogen molecules. We have a nitrogen molecule, that too of plus sign. So what it indicates? Plus indicates that the electron has been lost. Nitrogen molecules is going to lose one electron to form cation in general, I can say. As we know that cations are formed by loss of electrons. So plus 1 we have. So 1 electron has been lost. So nitrogen has 14 electrons. So see here, nitrogen has 14 electrons, whereas the nitrogen ion has totally 14 electrons. Plus 1 means 1 electron has been lost, therefore minus 1. So now we have to distribute 13 electrons in the energy level. So remember that nitrogen molecule has 14 electrons. Since we have plus 1 means 1 electron has been lost from the nitrogen molecule. Therefore 14 electrons we have, 1 has been lost, means 13 electrons we have. These 13 electrons has to be distributed. So as same as 1s and 1s, since 2 electrons we have, I will write in 1s 2 electrons and here in 1s also 2 electrons. Totally 4 electrons has to be distributed. So 1, 2, 3, 4. K shell is completely filled. So in case of 2s we have 2 electrons in the atomic orbitals, and here also we have 2 electrons. 4 electrons has to be distributed in molecular orbitals. So 1, 2, 3, 4. It's okay. So now in a 2p atomic orbitals. So totally 1, 2, 3, 4, 5, 6, 7, 8 electrons. Totally 13 electrons. Out of that 8 electrons has been distributed. So now in a 2p3 we have 3 electrons here and 3 electrons here. So in this case I mentioned 3 electrons, whereas in this case I mentioned only 2 electrons. So instead of mentioning 3 and 3, I mentioned 3 and 2, because as we know electron has been lost. And we know that the loss of electrons will be from valence shell only. Therefore 1 electron from 2p is going to lose. So therefore 3 electrons, and there we get 2 electrons. Totally in a p atomic orbitals, 3 plus 2, 5 electrons we have. 5 electrons has to be distributed in this section. So 5 electrons, 1, 2, right? Then pairing starts according to Hund's rule. 3, 4, and one more we have, that I fill here. So here we get a single electron, unpaired electron in case of sigma 2pz. So this is the change what you need to observe. When we have plus, 1 electron has been lost. I would have written 3 electrons here and 3 electrons here. Since 1 electron has been lost from valence shell, so 1 less electron I write here, and 5 electrons I am going to distribute here. We'll write the electronic configuration, and electronic configuration is K shell, these two are completely filled. Instead of writing sigma 1s2, sigma star 1s2, I write a K shell. You can write in this fashion also. Second one is sigma 2s2 and sigma star 2s power 2, and next energy level will be pi 2px2 and pi 2py over 2, and see here sigma 2pz we have 1 electron here, only 1, because in the sigma 2pz we have 1 electrons, therefore 1 I am going to write here. That is the electronic configuration. We'll see the bond order. Bond order is 1 by 2 into Nb minus Na. Number of electrons in bonding molecular orbital, number of electrons in anti-bonding molecular orbitals. So this is the bonding molecular orbital, this is the bonding molecular orbital, and these are all bonding molecular orbitals. So 1, 2, 3, 4, 5, 6, 7, 8, 9 we have. So number of electrons in bonding orbital is 9. Anti-bonding molecular orbitals, this is anti-bonding molecular orbital, this is anti-bonding orbitals, and these are anti-bonding orbitals. We don't have any electrons here, and 2 plus 2, 4 we have. So now I am going to write what actually the 4 here, and if you simplify this, what we are going to get here is 5 by 2 we are going to get, or you can write in the form of 2.5 also, 5 by 2 or 2.5. That is the bond order. Actually the bond order in a nitrogen molecule is 3, isn't it? N2 is 3, but whereas N2 plus is 2.5. So in a nitrogen molecule it is 3. After losing one electron, bond order converts into 2.5. So 2.5 is less than what actually 3. Therefore what I am going to say, N2 plus has less energy or less stable when compared to nitrogen molecule. And what about the magnetic property of this? So what I am going to write here is paramagnetic in nature. Paramagnetic in nature. Why it is paramagnetic in nature? Observe here, we have a lone pair of electrons, where we have in a sigma 2pz molecular orbital we have a lone pair of electrons, and lone pair of electrons if you have, and that shows the magnetic property in a particular paramagnetic in nature. So that is how MOT of NO2 plus can be explained. Example 8, oxygen molecule. O2, oxygen molecule. As we know, one atomic oxygen combines with one more atomic oxygen, we get the oxygen molecule. Atomic number of oxygen is 8, therefore electronic configuration will be 1s2, 2s2, 2p4. And for this oxygen, 1s2, 2s2, 2p4 will be the electronic configuration. 4, 5, 6, 7, 8. 8 electrons we have. 8 electrons from one oxygen atom and 8 electrons from one oxygen atoms. So totally we have 16 electrons. 16 electrons has to be distributed in a molecular orbitals of oxygen molecule. One very important concept you need to remember, as I explained the in general energy level of a molecular orbital theory, we have to change the molecular orbitals. If you consider boron, carbon and nitrogen, they are lighter elements. In that case, the energy level will be in a different fashion, and after nitrogen, the elements what we get, the energy level will be different fashion, energy level sequence. And one very simple I told you, if you just observe the previous example, nitrogen I was discussing, so here it was only one molecular orbital and here I have drawn 2. So I have just interchanged these 2 because that is going to be applied for lighter element and this is going to be applied for the elements after nitrogen. Oxygen we have, therefore first you need to fill sigma 2pz and later sigma 2px and pi 2px and pi 2py. I told you the reason also, where there will be overlapping of 2s and 2pz atomic orbitals takes place. For lighter elements you need to consider one molecular orbitals here and 2 molecular orbitals here, in case of 2p in particular BMO. Whereas in case of oxygen you need to interchange these, so I interchanged here. So now we'll distribute the 14 electrons and 1s2, 1s2, 2 electrons we have. Directly I write 2 electrons in the atomic orbitals, 2 electrons in the atomic orbitals. 4 electrons has to be distributed, so 2 electrons and 2 electrons. In a 2s also we have 2 electrons, therefore 2 I represent here and 2 I represent here. 4 electrons I distribute here. Now we'll come to 2p4 and 2p4. 2p4. Here 4 electrons I need to represent and here 4 electrons I need to represent. You need to follow Hund's rule. Pairing of electron starts after each atomic orbitals are filled with 1 electron each. So 4 electrons we have, so I write 1, 2, 3 and 4th one, now the pairing starts, therefore 4th one I write here. So similarly according to Hund's rule, 1, 2, 3 and 4 I am going to write. But remember, Hund's rule is going to be applied for such atomic orbitals which have same energy. So all these are 2p atomic orbitals only with the same energy, therefore I am going to apply the Hund's rule. Okay, so 4 electrons, totally 8 electrons has to be distributed. So here I write 2 electrons. So out of 8, 2 is over now. Now remaining 6. Okay, so 1, 2, 3 I write here, 4th one I write here. I have not represented 2 electrons in first 2px only, because remember pi 2px and pi 2py are of identical energy. So if we have identical energy, same energy, Hund's rule is going to be applied. Therefore 1 electron I write first, 1 more electron I write first. If I extra electron, then I start with the pairing. So 8 electrons we have, 1, 2, 3, 4, 5, 6, 7 and 8. So these two are also of identical energy, therefore single electron I am going to write here. So remember, Hounslow application is very important, and that is going to be applied when we have atomic orbitals of identical energy. That is how MOT of oxygen energy level I represented. So now I come to the electronic configuration. So K shell is completely filled, therefore K I write here, K shell of one oxygen, K shell of one more oxygen, K. Then we have sigma 2s, we have 2 electrons over here, and we have sigma star 2s. In that case also we have 2 electrons. Now we have sigma 2pz, so sigma 2pz, in that case also we have 2 electrons. Then we have pi 2px with 2 electrons. I will continue here, pi 2py with 2 electrons. Later we have observed there pi star 2px, we have 1 electron, therefore 1 I write here subscript. Similarly pi star 2py and 1 electron we have. The energies of these two are same. We can write first here and later here. The energies of these two are same here. So this is how the electronic configuration is going to be written. Now we'll calculate what about the bond order, which is going to be calculated by the formula 1/2 into Nb minus Na, which is equals to 1/2. We'll calculate number of electrons in BMO and ABMO. In simple, remember, where I mentioned star, that is ABMO. So any molecular orbital without a star is BMO. So here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 number of electrons in a BMO we have. So remember that BMO may be sigma bond, BMO may be pi bond. Okay, star if you mention, that would be the ABMO. Minus number of electrons in ABMO, star we have 1, 2, 3, 4, 5 and 6. So these are the ABMO, 5 and 6 we have. Therefore 10 minus 6 I will write here. Okay, and 10 minus 6 4 we have. 4 divided by 2, we are going to get 2. What this indicates, in between 2 oxygen we have 2 covalent bonds here, 2 covalent bonds, and the magnetic nature is paramagnetic in nature. So this oxygen molecule is a paramagnetic in nature. Why? Observe here in the molecular orbital, in the molecular orbital pi star 2px, pi star 2py, 1 electrons we have, they are unpaired electrons. Since the presence of unpaired electrons we have, therefore oxygen molecule is a paramagnetic in nature. That is MOT of oxygen molecule. Example 9, O2 plus ion. O2 plus we have, that is ion. As we know, in oxygen molecule we have 16 electrons. O2 plus 1 electron has been lost. Therefore the number of electrons in O2 plus here, in O2 plus the number of electrons will be, in oxygen we have 16 electron, plus 1 indicates 1 electron has been lost, therefore minus 1 I write. Therefore in O2 plus we have 15 electrons. So 15 electrons has to be distributed in the molecular orbitals. So 1s2 and 2s2, I have the same thing as it is, as same as the oxygen molecule. The only change we get in case of 2p atomic orbitals. So actually in case of oxygen molecule we have 4 electrons and 4 electrons, 4 electrons here and 4 electrons here. Whereas the given species is ion, that too O2 plus. So 1 electron has been lost. Therefore 1, 2, 3, 4 electrons are right here, and 1 electron has been lost. Therefore 1, 2, 3 electrons I represent. So how many electrons we have here? Here we have 4 and here we have 3, and 4, 5, 6, 7 electrons has to be distributed. So out of 7, 1, 2, 3, 4, 5, 6 and 7 we have. You got that one? So 7 electrons I distributed. Now we'll write the electronic configuration of that. So electronic configuration, K shell is completely filled, sigma 2s 2 we have, and sigma star 2s 2 electrons we have. And now see, sigma 2pz, there also we have 2 electrons. Next will be pi 2px, we have 2 electrons over there, and pi 2py, we have 2 electrons over there. And next what we have, we have pi star 2px, but we have only one electron. You can fill this one electron in place of 2py also, since the energy will be same. Now we'll see what would be the bond order in this particular species. So bond order is equals to 1 by 2 into number of electrons in BMO minus number of electrons in ABMO, 1 by 2 into BMO 1 2 3 4 5 6 7 8 9 10. 10 electrons we have in BMO. In ABMO 1 2 3 4 5. 5 electrons we have. 10 minus 5 5, you will be getting a 5.2, or you can write a 2.5 it is. Bond order of O2 plus is a 2.5 or 5 by 2. Then bond order of O2 molecule is 2. Okay, so 2.5 we have, means the energy of O2 plus will be more than oxygen molecule, you can say, and this is also paramagnetic in nature. Paramagnetic. This is also paramagnetic in nature. Why? Just observe, we have unpaired electrons in the molecular orbital pi star 2px. Because of that, we have a paramagnetic in nature. If you recall the oxygen molecule, we had the 2 unpaired electrons in these 2. So one electron has been lost from one valence shell. One electron has been lost here. That would be the MOT of O2 plus. Example 10, O2 minus ion. O2 minus ion we have. So if we'll see the electrons in oxygen molecule, one oxygen atom, one more oxygen atom will combine, will get oxygen molecule. Electronic configuration of one oxygen will be 1s2, 2s2, 2p4. Since atomic number is 8, for this also 1s2, 2s2, 2p4, and 8 electrons are from these two. Totally we have 16 electrons. So 16 electrons we have in oxygen molecule. So now observe, the given species is O2 minus. Plus indicates loss of electrons, minus indicates gain of electron. In general, we know anion is formed by gain of electrons. 1 minus we have, means 1 electron has been gained. So we have totally 16 electrons, but if you consider O2 minus ion, in this case 16 electrons we have already in oxygen, but 1 electron has been gained plus 7. Therefore the number of electrons will be 17 electrons. So we have to fill 17 electrons in the molecular orbital of O2 minus. So 1s2, 2s2, 1s2, 2s2, we have 2 electrons each. I filled that already. Now the very important part is 2p4 and 2p4. So here we have 4 electrons and here we have 4 electrons. Let me show you that. 1, 2, 3, 4 according to Hund's rule. So 1, 2, 3, 4 according to Hund's rule. So this is how 16 electrons are filled. But we have one more electron. So one more electron has been added. We know that the addition of electron takes place in a valence shell, and the corresponding energy released will be electron affinity. This concept we know. So in the valence shell, one electron has been added. You can represent anywhere. I am going to represent here. So one electron we have added there. One extra electron we got. Therefore total number of electrons will be 17. So totally 1, 2, 3, 4, 8 electrons has been filled here. So from 1s and 2s. So now we have to distribute to 2p and 2p. Totally 4, 5, 6, 7, 8, 9 electrons we have. So 9 electrons has to be distributed in this 2p section here. So 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. When we have identical energy atomic orbitals, Hund's rule is followed. Therefore, 9 electrons are filled here. Now you see, in a pi star 2px we have 2 electrons, whereas pi star 2p we have a single electron. So this is actually the unshared pair of electrons, I can say. We'll write the electronic configuration of this species. K shell is completely filled. K shell and K shell are right. Next we have sigma 2s. 2 electrons we have in that molecular orbital. Sigma star 2s over 2 I write here. Next molecular orbital will be sigma 2pz over 2 I write here. Next will be pi 2px. In that MO also 2 electrons we have, and pi 2py, here also we have 2 electrons. Now observe the next one, pi star 2px, I have 2 electrons here, pi star 2px, 2 electrons, and one more we have, that is pi star 2py, but here we have 1 electrons. If you count the number of electrons, that should be exactly 17. Then what about the bond order of this species, which is going to be calculated by the formula 1 by 2 Nb minus Na, 1 by 2 number of electrons in bonding molecular orbitals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons we have in a BMO, and ABMO unit to calculate 1, 2, 3, 4, 5, 6, 7 we have. So 7 we have. 10 minus 7 we have 3, or I can say 3 by 2 you are going to get, or I can write 1.5. That is the bond order of O2 minus. O2 minus bond order is 3 by 2. So remember that previous one O2 plus the bond order was 5 by 2, and here it is 3 by 2. Actually for oxygen molecule the bond order is 2, and for O2 minus the bond order is 1.5, means less than 2, less reactive or less energy you can say. And this is paramagnetic in nature, isn't it? This is also paramagnetic in nature. Try to understand why it is paramagnetic in nature, because in a pi star 2py molecular orbital we have unpaired electrons. Because of unpaired electrons, paramagnetic nature arises. Remember, O2 molecule, O2 plus and O2 minus, the bond order is different. In O2 it is 2, in O2 plus it is 5 by 2, in O2 minus it is 3 by 2. That is the MOT of O2 minus. Example 11, O2 2 minus. We know in oxygen molecule we have 16 electrons, but the species is O2 2 minus. Minus indicates oxygen molecule has gained electrons. 2 minus means 2 electrons has been gained. So in O2 minus species, O2 2 minus ion, oxygen contains 16 electrons, but 2 electron has been gained. Therefore total number of electrons will be 18. So 18 electrons has to be distributed. So 2s and 1s atomic orbitals, molecular orbitals I filled already, because the very important thing is 2p and 2p here. So let me write 1, 2, 3, 4 electrons, and 1, 2, 3, 4 electrons. This is for the oxygen molecule, but 2 electron has been gained. Okay, so 2 electrons has been gained. Therefore 1 electron I write here and 1 electron I write here. Totally 1, 2, 3, 4, 5 electrons we have, and here also 5 electrons we have. Totally 10 electrons has to be distributed in a 2p section. Totally 10. Therefore 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons I filled. In these two cases, Hund's rule I followed. That would be the energy level diagram of O2 2 minus. Electronic configuration of this K shell is completely filled, 1s and 1s2. Therefore sigma 2s, 2 electrons we have in this MO. Sigma star 2s, we have 2 electrons in this MO. Next we have sigma 2pz, we have 2 electrons. Next we have sigma 2px with 2 electrons. Next is pi 2py with 2 electrons. Next we get anti-bonding pi star 2px with 2 electrons. Similarly one more pi star 2py with 2 electrons. That would be the electronic configuration of this species. We'll see what about the bond order. Bond order can be calculated with the formula 1 by 2 into Nb minus Na, which is equals to 1 by 2 number of electrons in a BMO. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons we have in the BMO minus ABMO. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons we have. 10 minus 8 we get 2. 2 divided by 2 we get 1. What this indicates? In between these two O2 2 minus we have only one covalent bond, and this is the diamagnetic in nature. Diamagnetic in nature. Why this particular species is diamagnetic in nature? Observe the MOs, and here we don't have any unpaired electrons, because of absence of unpaired electrons, this O2 minus is diamagnetic in nature. So now remember, bond order of O2 molecule is 2, bond order of O2 plus is 5 by 2, O2 minus is 3 by 2, O2 2 minus is 1. What I am going to say, O2 2 minus will be less stable when compared to oxygen molecule as well as O2 minus ion. That is the MOT of O2 2 minus. Example 12, Ne2. Neon it is. One neon atom combines with one more neon. We get a Ne2 molecule. Atomic number of neon is 10. Therefore, the electronic configuration will be 1s2, 2s2, 2p6. And here also 1s2, 2s2, 2p6. If you observe the valence shell, we have 8 electrons. Noble gases, this particular element belongs to 18th group element. So 10 electrons from this neon and 10 electrons from this neon, totally we have 20 electrons. This is a molecule. We don't have any plus or minus either to lose or to gain electron. This is a molecule. Therefore, totally 20 electrons we have, and 20 electrons has to be distributed in this MOT. So first I consider 1s and 1s. In 1s we have 2 electrons, and in 1s also we have 2 electrons. Totally 4 electrons has been distributed in this MOT. Therefore, 2 electrons will be here and 2 electrons will be here. Next I talk about 2s2 and 2s2. Here I have 2 electrons, and here also I have 2 electrons. 4 electrons I am going to distribute over here. In a 2p and 2p, totally we have 6 electrons. So follow the Hund's rule. 1, 2, 3, 4, 5, 6. Completely filled 2p we got. And here also 1, 2, 3, 4, 5, 6. Completely atomic orbitals we got. So 6 electrons we have here and 6 electrons we have here. Totally 12 electrons has to be distributed in a 2p section only. Totally 12. Just see how I am going to fill that. Out of 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 electrons I filled, and here I followed the Hund's rule. 12 electrons means all the molecular orbitals are completely filled in case of Ne2. We'll write the electronic configuration of that. So electronic configuration, since K shell is completely filled, therefore KK I write. Next we have sigma 2s. We have 2 electrons over there, and sigma star 2s with 2 electrons. Now you come to the next one, that is sigma 2pz with 2 electrons. Next we have pi 2px with 2 electrons, this one. Next we have pi 2py with 2 electrons. I will move to the next molecular orbital, pi star 2px with 2 electrons, and pi star 2py with 2 electrons. Next one we have sigma star 2pz with 2 electrons. That is the electronic configuration of Ne2. So this is how we can write the electronic configuration. If you refer some reference books, sometimes they mention equal sign in between these two. So let me consider, they mention equal sign in between these two, and in between these two they are going to mention equal sign. Why? Because the energy levels of these two are same. Remember that one. So you can mention it and you can leave that, but you need to write the electronic configuration, the correct energy sequence here. So bond order will calculate, and the formula for that is 1 by 2 into Nb minus Na. Will calculate number of electrons in a BMO. See here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons we have in BMO, means the molecular orbital without star. Now ABMO, where we have star, you need to consider all these. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in ABM also we have totally 10 electrons. And what would be the bond order? Bond order we got 0. what it practically indicates, there is no covalent bond present in between Ne and Ne in a molecule of Ne2. What I am going to say, since bond order is 0, so this molecule does not exist in nature. It is highly unstable, I can say. So since it is highly unstable or does not exist in nature, there is no question of magnetic property of that. That is the MOT of Na2. Now I am going to summarize molecular orbital treatment of homonuclear diatomic molecule. 12 examples I discussed. Know that all of these 12 examples are homonuclear diatomic molecules. Homonuclear, same kind of a nucleus we have, same atoms we have in a particular molecule or ion, and all these are a diatomic molecule. Atomicity will be 2. The molecule whose atomicity is 2, we call it as a diatomic molecule, and all these are homonuclear diatomic molecules only. So in general, I summarized the molecule or ion, and in the second column I considered bond order, and in the third column I considered magnetic property of that. If you want to calculate a bond order and the magnetic property along with the electronic configuration, it is compulsory to know the energy level diagram of that. So in energy level diagram, as we know, usually we start filling up of atomic orbitals from 1s, 2s and 2p according to Aufbau principle. As we know, electrons are going to be filled in the increasing order of energy of the atomic orbitals, that we call it as Aufbau principle. And we came to know the electrons are filled in the atomic orbitals by following Pauli's exclusion principle. Only electrons of opposite spin can be paired. Therefore, if you consider that, so this is the one electron with one spin, and this is the one more electron of the one more spin, that too opposite here. So only electrons of opposite spin we paired in all atomic orbitals as well as molecular orbitals. One more rule we have to follow, Hund's rule. If you have atomic orbitals of identical energy, in that case pairing of electron starts after all the atomic orbitals are singly occupied with electron. So if you consider this particular 2p, to px, py, pz, all are of the identical energy. Therefore Hund's rule has to be followed in such cases here. So by following these standard rules, we are supposed to fill the electrons in molecular orbitals. We know these are the atomic orbitals, these are the atomic orbitals, these are the atomic orbitals. In the middle we have molecular orbitals. Atomic orbitals combine, we get molecular orbitals. When atomic orbitals combine, we get two types of molecular orbitals. One is BMO and one more is ABMO. ABMO is unstable, whereas BMO is stable. Energy of BMO is less, energy of ABMO is greater. Therefore in the MO diagram we write BMO below and ABMO above. Therefore this is also BMO, this is ABMO. In a 2p, these three are BMO and these three are ABMO. For ABMO antibonding, we represent a star in that manner to identify that one. BMO may be sigma and BMO may be pi also. Similarly, ABMO may be sigma and ABMO may be pi. As we know, if there is head-on overlapping of atomic orbitals, sigma bond is formed, and sideway overlapping of atomic orbitals, pi bond is formed. All these are the theory what we discussed. So in the same manner, electrons has to be distributed, and based on that we write the electronic configuration. Electronic configuration in general we write 1s2, 2s2 and so on, whereas in case of molecular orbital theory we mention sigma 1s and the number of electrons, sigma star 1s number of electrons. So similarly in this fashion we are supposed to fill the electrons in the molecular orbitals. That is the energy level sequence. In general, the energy level sequence will be sigma 1s, sigma star 1s, then sigma 2s, sigma star 2s, sigma 2pz, sigma 2px, sigma 2py, then pi star, sorry, these two are the pi, and pi star 2px, pi star 2py, sigma star 2pz. Whereas if you consider lighter elements like boron, carbon and nitrogen, these two are supposed to interchange. I explained this. So these two has been interchanged in case of boron, carbon and nitrogen. Usually in case of boron we have no need to consider 2p electrons, because all they are usually in case of the first hydrogen, lithium, beryllium, the p orbital is not required, whereas in case of boron and carbon and nitrogen, p orbitals are required. These are lighter elements, therefore we need to write these pi 2px, pi 2y below and sigma 2pz allow, or interchange we have to do. So after nitrogen, oxygen, neon, whatever we get, and this is the fashion what we write. This is the very important thing you need to know. Don't get confused with that one. Usually we have drawn this one. So usually in case of a nitrogen, N2, N2, C2, and we used that one. Usually in these cases, what is that? C2, N2 and N2 plus, we interchanged these two, and for the remaining from after nitrogen plus, we use the same, and two molecular orbitals here and single molecular orbitals here, and that is for the lighter elements. You need to know about that. And by mentioning the energy level diagram, later we arrange the electronic configuration and we calculated the bond order. Bond order is nothing but number of covalent bonds present in between the atoms of a molecule, and that is calculated by a formula, that is 1 by 2 into Nb minus Na. Number of electrons in BMO minus number of electrons in ABMO, and we calculated the bond order. And later on, if there is a presence of unpaired electrons in the molecular orbitals, we say it as paramagnetic. If there is absence of unpaired electrons, and that we say it as the diamagnetic in nature. Based on this, we solved 12 examples for that one. In general, see, hydrogen molecule, the bond order is 1, and that is diamagnetic in nature. In case of He2, the bond order is 0. What it indicates? He2 molecule does not exist in nature, or you can say that is monoatomic. Helium will exist as helium only, not helium 2, He2, because bond order will be 0. In case of Li2, the bond order is 1, and that is also diamagnetic in nature. In case of Be2, bond order is 0, does not exist, and C2 bond order is 2 and diamagnetic in nature. In a nitrogen molecule, bond order is 3, diamagnetic in nature. Nitrogen plus, the bond order is 5 by 2, paramagnetic in nature. See here, 3 we have, and O2, N2 plus, it is 5 by 2. In case of oxygen, the bond order is 2, paramagnetic. O2 plus, the bond order is 5 by 2, paramagnetic. O2 minus, 3 by 2 and paramagnetic. O2 2 minus, bond order is 1 and diamagnetic. In case of Ne2, 0, the molecule does not exist here. So you need to remember the bond orders, and using bond orders we can explain some other properties. What is that? In short, I have written, when the bond order increases, bond enthalpy also increases. Bond enthalpy, energy required to break the bonds. In short, we call it as bond enthalpy. And bond length decreases and stability increases. How these four are interrelated? Try to know. Bond order increases, bond enthalpy increases, then the bond length decreases and stability increases. So one example I consider, if you consider carbon single bond carbon and carbon double bond and carbon, when you move from here to here, bond order increases. So when bond order increases, bond enthalpy increases. Therefore, bond enthalpy of this one is greater when compared to this. Then bond length decreases. So bond length will be maximum here, bond length will be minimum here. When bond length decreases, stability is also increases. In general, when a bond order increases, stability also increases. If this you know, we can compare the stability of these. So see here, now I consider nitrogen. Bond order is 3 and bond order is 5 by 2. So bond order is of N2 is 3, whereas N2 is 5 by 2. So 5 by 2 is nothing but a 2.5. So when you compare N2 and N2 plus, the bond order is going to decrease. So when the bond order decreases, the stability also decreases, isn't it? You compare oxygen. Here it is 5 by 2. Okay, so 5 by 2 is nothing but 2.5. 3 by 2 is nothing but 1.5. So it is 2. So when you compare O2 and O2 plus, it is 2.5. Therefore, O2 plus is more stable when compared to O2. When you compare O2 minus, since it is 1.5, so O2 minus is less stable when compared to what? O2 here. Then O2 minus, if you see, the bond order is 1. Therefore, O2 minus it is, you know, the less stable when compared to 1.5 and when compared to what actually 2, but it is more stable when compared to this one Na2 it is 0 and there is no existence of this molecule. So remember that when bond order increases, stability increases, and similarly we can explain bond enthalpy and bond length also. That is all about the molecular orbital treatment of homonuclear molecules and some ions I discussed here. So you need to summarize these bond order and magnetic property as a point of IIT JAM examination and GATE examination. If you see previous year question paper, the probability of questions from molecular orbitals of these are highly preferred, highly important one. Therefore, I solved as many examples as possible here. So you need to remember the bond order in this fashion directly, because in the examination we don't have so much time to draw the energy level diagram, to calculate and to get the bond order. Therefore, you remember the bond order in this fashion. In the next session, I am going to talk about molecular orbital treatment of heteronuclear atoms. Heteronuclear molecules, we have more than one atoms. Examples like carbon monoxide, nitrogen monoxide and NO+. What will be the molecular orbital treatment of these heteronuclears? We are going to study in the next session.